We all have listened about particles, the universe, maybe some Nobel Prizes, and many other things related to physics. But how does it really affect our lives? Today, Dr. Paganis and we both are going to make the science behind it edible for everybody. Así que toma pulque y come nopal, que el Pulque Podcast va a comenzar. It's my pleasure to welcome Dr. Paganis. Dr. Paganis, good afternoon.
Hi, good afternoon. Thank you for inviting me here.
No, thank you very much. Dr. Paganis, how would you describe yourself? Can you tell us a little bit about yourself? I know that you studied physics in the United States. Can you tell us a little bit more?
Yes, actually, I was from training, from undergraduate. I'm an engineer. I studied electrical mechanical engineering, like many people, and then I liked physics. So I went to CERN actually as a summer student in 1991, and I fell in love with particle physics. So then I applied and for a PhD. I went to America, that back then many people did.
In Texas.
I went in Texas. I didn't apply to many places because back then, you need to pay money to apply, pay the fee. So I could have applied to other places. So I didn't apply to many places. So at Texas, there was Weinberg, the person who did the modern particle physics, what we call the standard model of particle physics. And so it has a Nobel Prize. So I was attracted by this. But I was an engineer. I was not a physicist yet. Yeah, so, so it's interesting that America has this plus.
The system
that even if you are from a different discipline, you can quickly
jump to another one.
So I think, I even have students now that they ask me exactly the same question. I'm an engineer. Can I do particle physics or some physics? I said, yeah.
Why not?
Why not?
And Professor, what drove you to move from the United States, being a PhD student, to go to first Switzerland and then come to Taiwan to become one of the professors with more papers published in high impact websites and things like that? I mean, you have more than 1,000 publications. Can you tell us a little bit of that schedule?
Yeah, actually, after I finished my PhD, I actually went to Columbia University. So I went to New York, downtown New York. So basically, I rented a place very close to Broadway Street. So it's very cool. Back then, it was so nice. I don't know about now. And our experiment was not, the experiment we did was actually in Europe, but not in CERN. It's not in Switzerland, but in Germany.
Oh, in Germany.
In Germany. So there in Germany, we were using basically electrons to explore what happens inside the protons and look for new physics and so on. So actually, I started living there in New York. And that was before the 9/11 incident. I was lucky enough to actually move to Germany.
Yeah.
And never went back to actually America. Around year 2000, I left. I moved in Germany. Permanent. It happens to be permanently because the laboratory was there, and I just never went back. And then from Germany, I went to. I spent 3 or 4 years in Germany, and then I went to join the Atlas experiment at CERN in Geneva.
Are you Native American? Because I'm a little bit curious about your name status.
No, I'm actually originally from Greece.
Okay.
Yes. So So I'm from Greece. So in my time there was no internet or this kind of things. When you applied to go to graduate school, it was an adventure. You didn't know much. My family didn't know anything about how to help me, or it was from other colleagues finding out how to apply to go to study. To go to do a PhD in America. So yes.
Status sounds a little bit like statics.
Yes.
Is it the?
Yes, it's in Spanish. Is I think Eustacio.
Eustacio. Okay.
Eustacio. That's my name. It means a stable person.
Stable person.
Stability, basically.
Stability.
Yes.
So maybe we can say that you were born for physics.
No, I just happen to have a weird name.
Okay.
Very physics name.
And okay, let's keep on going. At CERN, what was your work? What did you work in?
Yes, I was definite from the beginning. I wanted to work on the Higgs. Yes, the Higgs boson.
Yeah. Were there some other research already going on it?
Of course, yes. When I went there in 2003, and back then we were also building and designing the detectors or optimizing the detectors to discover the Higgs.
Yeah.
So there are two experiments that looked and discovered the Higgs, the ATLAS experiment and the CMS experiment. Although there are 4 experiments at CERN, the 2 of them looked for the Higgs.
CERN, for everybody, like the meaning of CERN, it's in French and it's Conseil Européen pour la Recherche Nucléaire.
Yeah.
That would be in English, European Organization for Nuclear Research.
Yes.
And the Atlas, it's LHC apparatus.
Yes.
And CMS is a contact muon
Muon solenoid. Yes.
solenoid. Okay. And how long were you involved in this research?
I started working on the Higgs in 2003, and I'm still working on the Higgs. Although I changed experiments when I came in Taiwan, because
Yes.
that university here was in CMS, so I had the option to go to another university in Taiwan, but I decided to go to what I think is the best university in Taiwan. So I had to change experiments, which was difficult for me, but now I think it pays off. Now I'm happy. I didn't want to change experiment.
Yes.
I liked my previous experiment, but sometimes we change and it's uncomfortable, but that's what I did and it worked.
What do you think about people calling the Higgs boson the God's particle?
Yeah.
Like personally, I know that Francois Englert, the one who got the Nobel Prize, he doesn't like this nomination. What do you think about it?
Yes,
Or
maybe.
why do people call it that way?
Maybe historically there was a professor that in the early 70s he called this the goddamn particle.
The
So it was not
particle.
called the God particle, but he added in a foul word, and then that remained. I think that because that professor called it this way, people removed the foul word, and then it was left as God particle. There's no relation to God, of course. I think it's just a very important particle, maybe the most important we have discovered.
Why?
Yeah, because why? Because it solves several very important issues in physics, very fundamental issues.
Yes.
To give you an example, all the particles we know they have masses, but mass, according to Einstein, is a very terrible thing. Yes, and it creates problems to our equations, and so most of the physicists we believe that there are no masses. When
Mass doesn't exist.
mass doesn't really exist, it's kind of an interaction or some energy that slowly the particles we see now, this particular energy or this particular interaction gave them mass. So behind the elementary particles mass, we have the Higgs boson doing the job. This is what interacts with them to make them look like they have mass.
They've got mass.
Yes, but this is not the only problem.
Yes.
There is another even more serious issue, the fact that all interactions are carried by certain particles. For example, the electromagnetic interaction is transmitted by photons.
Yeah.
And physics tells us that these photons must be zero mass. They shouldn't have mass. Okay? And
As well as gluons.
as well as gluons that transmit the strong interaction, they shouldn't have mass, and indeed they don't have mass.
Yeah.
But there is a third interaction, there is another interaction that is called weak nuclear interaction, is the reason why the CERN burns so slowly, and
Okay.
so we're alive. It's a very important interaction for us. But this particular interaction, actually, the particles that carry it, the W and the Z bosons, they are heavy, they have mass. So it's very weird, yes?
May I say and let's say repeat what is the process that is being in the sun or on the sun? It's there are many hydrogen atoms.
Yes,
that
there are nuclear
interacting?
interactions or radioactivity. The nuclear interactions and the radioactivity, let's say, responsible force is this weak nuclear force.
Yes.
And this weak nuclear force is weird because the particles that transmit it, that were discovered, by the way, at CERN, in 83, so actually recently, these particles are heavy. That's why we couldn't see them, because they're heavy, and heavy means short-lived. So the reason they are heavy is, again, the Higgs. Only the Higgs could explain why they are heavy and why the photon is light. So because only the Higgs could do all this weird job, it was put in the standard model to do this job, and then we hadn't discovered it because we didn't know what the mass of this Higgs is. Yeah.
I know that something else that is very light is dark matter.
Yes.
And many people, I think that almost everybody have listened about dark matter. Can you, from the point of view of a physicist, tell us, or an engineer, tell us?
Yes. What dark matter is, I think it is, or why it's light, or what?
Both. We've got time.
Yes. So basically, we don't know what dark matter is. We don't even know if it is a particle.
Okay.
But how do we know it exists is because we look at this is astronomical, yes? We look at the galaxies. This is not really particle physics. You look at the galaxies and you see that the way the galaxies are rotating indicates that some mass is missing. Actually, a lot of mass, like 75% of the mass should be there to explain the speed of the rotation of the spirals of the galaxies.
Yes.
The mass is missing, but should be there. And then we don't observe this mass, so we started suspecting there must be some kind of particles there that they don't interact with anything, and we called it dark matter.
But how come if they are light,
we don't know,
can they be 30-25%? So dark matter hadn't been very researched?
Yes. So the initial idea was these particles are some heavy, slow particles, heavier than, like proton mass, 1 GeV is the proton mass, or heavier, even 1,000 times heavier. And we suspected that, people suspected that this has something to do with new theories beyond the standard model of particles that we know now, like supersymmetry. It was a good theory that was predicting this kind of particles.
Yes.
I cannot explain why, but yes, some theories predict particles that do not interact with anything else. So these are good candidates of dark matter. But we didn't find them.
Yes.
We didn't find them. We looked for them and still looking. But after all these years, different experiments all over the world, including ATLAS and CMS, and underground experiments, they haven't found any of these. So now people believe that dark matter may be actually a very light particle.
So let's say a real life example of how does these particles don't interact with other ones would be right now me holding my glass.
Yes.
My particles are interacting with the glass particles.
Yes.
But see, if the glass was dark matter, in a way, I would across.
The dark matter now goes through this room, through the water, through you, and
it goes
there's no
through,
interaction.
So it doesn't. We cannot touch it.
Cannot touch it, cannot interact, cannot put detectors to find it, except that in certain model of physics, including the standard model, certain models of physics, we expect that there may be a small electromagnetic, for example, interaction between dark matter, very, very, very small interaction between dark matter and matter, normal matter, or electromagnetic fields. For example, there are people who put very strong magnets or magnets, and expect some small interactions between dark matter and these magnets sitting in this room, a magnet sitting in this room, and they try to see some radiation coming out. Okay, and that will be maybe an indication of dark matter. So there are many experiments like that happening now, but nobody has seen anything yet.
How about if you start building a novel device like
Yes.
I know you are researching about
Yes.
building a novel device at the CMS at CERN.
Yes, actually, this novel device that we try to build at CERN is not for dark matter, but you can build novel devices even in Taiwan, nothing to do with CERN. Novel devices that include cryogenic and equipment that is even used in quantum computers, like special amplifiers and special circuits, cryogenic circuits. Put them in some magnetic fields, and with these devices you can look for dark matter, but you can look only in certain energy ranges, not everywhere you like. So right now what we do here in Taiwan, we try to find a method to look for dark matter in large energy ranges.
Yes.
Small energies, but in a large energy range, not only in a small window of energy. That this is what people do now. They look only in small windows of energy.
How big is this window? And let's say the ratio of the usual ones and the big ones.
Oh, it's
An
orders
estimation?
orders of magnitude, 10 to the 10th.
Oh, so
10
it's-
orders, yes. So actually now we're looking in very small windows, because basically, I don't know if you know as engineers about resonances. You know, you have resonating cavities.
Yes.
That the electromagnetic field resonates there. So you build a cavity here too. In these experiments, you build a cavity, and then you can only be sensitive on something resonating in this
resonance.
cavity. Yes,
Yeah, yeah.
not then. You have to build bigger or smaller cavities to get the rest. So we want to go around. People are trying now to go around this problem.
So that's a project here in Taiwan.
Yes, there are projects here. You can do them locally, but there are also projects that are more global, and they are looking in the sun, because these particles may also be coming from the sun.
Okay.
Dark matter can be produced in the sun. For example, there are theories like this. So people build some.
Such as photons.
Yes,
Because every day we get these photons from the sun.
they are like photons, but they are not. The photons are produced in the.
It's a like.
Yes. But they produce photons. That's the beauty of these. In a magnetic field, they can produce photons. The
Dark matter
yes,
can produce photons.
in a magnetic field. That's the idea everybody uses now. Yes.
That's very, very interesting.
Yeah, it's cool.
And-
It's really cool. Yes.
So tell me a little bit more of that project that you have of founding the Taiwanese Instrumentation Detector Consortium.
Yes.
That the main goal is to develop another types of experiments here in Taiwan.
Yes. So I think that goes back to your question you asked me earlier about a detector, a big project a detector we built for CMS.
Yes.
So when I came to Taiwan, we propose this new technology to build it here in Taiwan. There is a new technology called high granularity calorimeter. This is a buzzword. It's a detector that detects photons, electrons, pions, all sorts of particles, jets of particles. This is a very fine granularity detector. That means it looks like a 3D camera, and it can
Okay.
see the particles. They can see the particles interacting in that camera and making showers, and you can see very fine detail. And then you can decide if this is something new particle or something that is ordinary particle at CERN in Geneva. So this will be built, the heart of the detector will be built in our labs that we developed, and we are very proud. Over the last 5 years since I came here, we developed this in collaboration with Zhongyan Dashi,
Zhongyan.
and NCU, and Academia Sinica, John Yen. And now other people are jumping in. So that was the start, that project. So basically, because we had that project and we started building things here and being very successful in Geneva, people say, oh, why don't we do other experiments too? MIT, for example, came and asked us to build a detector for Brookhaven National Laboratory.
Yeah.
And the University of Tokyo came and visited here, and we demonstrated how we build these things. And so this is not my research. This is my colleague's research.
But you are the founder of it.
Yes, I'm the person who started thinking it's good to have a laboratory here. Not for this necessarily. So anyway, this thing is now growing, and the Department of Energy of Taiwan, the Department of Energy, wanted us to make a consortium, which means to make a lab that is shared by the whole Taiwan. And then every university that has a similar lab, we can actually go and use it if they have some speciality.
Is there any specific location already?
Yes, so the center of this, the core of this facility is here in Tianshuguan, the Astromath building.
Okay, in
Yes.
NTU?
Yes, in NTU, but We have laboratories now also in NCU, Zhongyang Daxue, that they do specific things. We have robotic capabilities here to build detectors. They don't have, but they have other capability. And Academia Sinica is putting a very fancy laboratory, machine shop, that they have CNCs, and they can build mechanical parts that are hard to build here. We can build them there. So that's how we started. So that is, the beauty of that is that we don't want to go and build things outside Taiwan. We want to build things in Taiwan, and when we need some PCB, for example, something useful for our detectors, we can go to a local company to build it. We don't have to go buy it from Italy. Although we love Italy, but we prefer to spend taxpayer money back in Taiwan. This is the biggest goal.
So is this being founded by Taiwanese, let's say, enterprises that would be interested in some type of technology? I mean, in the future, what are gonna be the, let's say, how does it will affect our life?
Okay.
Our future life.
This is a very, very difficult question because although I can give you some examples, it's a very difficult question because even when electromagnetism was and Faraday's law by Faraday was discovered, Faraday himself said, "Oh, I'm not sure how this theory is going to apply in real life." And today we have engines in the cars, and you have engines, yes, which is motors, yeah. That happened 100 years or 200 years later, yes. So there may be big benefits of this research that come later, and I cannot tell you. But right now, for example, the Higgs research, yeah. But right now, building devices, we have an immediate gain. For example, we can build devices for proton therapy applications, medical applications. One big example is PET.
What is the meaning of PET?
PET is a device that uses positrons emitted from your body. You put in your body some very weak radioactive source.
Yeah.
And you can do imaging. For example, if you have a certain part of your body that you want to check for cancer, not if you have cancer, but if you will have cancer in the future, this PET...
so it's preventing.
It is preventing, exactly. It can tell you if these cells look weird. It does a time-dependent imaging, not only picture, but also time-dependent imaging of your cells. So actually, this device that looks actually like a small CMS is my experiment at CERN. It looks like a mini CMS. It looks, you put it's not an MRI. You put your body there, and it can predict to 90%, 95%, it can predict cancer. It can predict. It's expensive, but it's basically something that in the future, it will be more approachable to most of us. So we can actually not wait, go do the exam and see if there is something there, and we can take the right actions to prevent cancer from appearing.
So the early results will be seen in health. In human health.
Yes, because the devices we are producing are more kind of imaging devices, and very fast electronics. So they apply very well in doing imaging. But there are many other applications. And right now I cannot cover the full range of applications. We actually encourage our students and people who work with us to come up with inventions, new ideas, how to use the stuff we're developing, including software, to come up with a new idea that is applicable, that has an application, invention, basically.
So you promote innovation, creativity.
Yes, this is the point. It's not only doing basic physics. We are doing basic physics for the good of the public. This is something that people don't understand, but we're not engineers in engineering. We're doing basic physics, basic research, but I really believe basic research without application is strange. We should encourage our students to do both. And our researchers, it's not only the students. Yes.
So let's say for the future, for people who are going to be graduating I don't know, in 5 or maybe 10 years, that they are already have like they already want to go to a physics area or an engineering area. What's your opinion of that? What's
Oh, it's great. I mean, I don't know very well now the PhD in engineering, how different it is from our PhD in physics. I think they are similar actually in the experimental work, yes? I will give you an example. My student that just graduated last year, Jia Hong, very good student. He was from Taida and then he came to do a master's with us and he worked on exactly what I described, this project,
yes,
this detector for CERN. Now he has a very good job here in Taiwan. He's doing cryptography. Cryptography, yeah. Actually, the biggest client of his company is a private company. The biggest client is, I think, Taiwanese army or security stuff. So, and these are very interesting stuff because they do actually hardware, not only software, but they are developing hardware. So, the training you get in engineering or physics PhD, for example, I think, is so broad that you can do crazy things. You can go and do something that you never imagined you would do. So I think that's you don't learn one thing. You learn many things.
I think it is Neil deGrasse Tyson,
Yes.
the one that said, you only need one question. And once you answer this question, you think you already know enough
Yes.
about a subject. But once you think you know enough about a subject, it's enough for you to know that you don't know enough about that subject.
Yes. That's what we think also. So you will see actually in our field many humble people, in particular experimentalists, that because you realize you don't know much.
I'm in front of one for sure because I think you are someone incredible, Dr.
No.
Pagani. And I would like to know a little bit more of the events that you are gonna be holding for university students and people that are interested, let's say, in this Taiwanese consortium,
Yes.
to attend, to know. Do you
Yes,
know
so-
about any events coming?
Okay, now we are in difficult times with the
COVID?
and because we do international, there are many international events that involve not only Taiwanese but also people from other countries come here, and we have events like this. The closest events we have are in January. Yes, many students will be involved in presenting their work in this consortium that is actually a meeting about this consortium and the future of high energy physics in Taiwan. So in this, we actually want to plug in many very young students, including maybe undergraduates. So actually it's very well attended by many young people who may want to see what we plan to do in the future in Taiwan. So I think it's very nice to have laboratories all over Taiwan or all over the world, not kill the laboratories in the universities, because it is something I saw in England. The government, when I was there, liked to close down the laboratories in the various universities and keep them more in the national labs, like John Yuan Yan here. Yes, I think the laboratory should be there for guys like you to go in the laboratory and build detectors, do your research. They should be there. And high energy physics is an area that I'm worried a little bit that if it's not supported appropriately, we will lose these laboratories, and then there will not be enough laboratories to learn physics, basic physics, or train talents like you guys in the best schools we have in the country. Yeah, it's a very risky situation, and I think what we are trying to do is to actually promote the laboratory.
Okay.
Yes.
And just to conclude, Doctor, I remember a lot. I mean, here in Taipei and in NTU, we have beautiful sunsets. And I remember a lot your class that you told us about this physics. You explained us the physics behind it.
Yes.
Can you share with us a little bit more of that?
Yes, I mean, I think many people know about this. It's a standard question in the undergraduate, but people still like it, is why the sunsets are red.
red or
yes, why the
shades of orange.
or yes, or they have all these beautiful colors, and why, when you look in the sky is blue. This is very strange. Yes, I mean, what happens is it's a bit quantum mechanical. What happens is that the light that comes from the sun is white because it has all these colors, but when the light goes through the atmosphere, the blue light, which is the highest energy part of the spectrum, scatters more. So the blue light scatters more and the red light scatters less. So when you look in the sun, in the sunset, the blue light has been scattered away.
Yeah.
And what you see is red, more and more red. Now the sky is blue because the blue light is scattered away from the sun. So when you see in the day, like today, you see in the sky, you see blue. If you look away from the sun, you see blue because basically the blue light has been scattered away. When you look in the sun, you still look white.
Yeah.
It looks white. It doesn't look red. Yes, it doesn't look red because simply there is not enough atmosphere to make you start seeing the red. You have to look in the morning or in the sunset where the light goes through a big chunk of atmosphere before it comes to your eyes. Yeah. So beauty has to do with physics, of course, again.
For sure.
For sure.
Thank you very much, Doctor.
Okay.
This will be it for this podcast. And
Okay.
I hope everybody of you enjoyed it. Thank you very much, Professor.
Okay, thank you for inviting me here.
Thank you.
It was a pleasure.
Okay. Thank you very much for watching this episode. Like the video in case you liked it and leave a comment below for further improvement of our content. As well, if you like topics such as new technologies, research done in universities, or even stories of wonderful people, subscribe to our channel. You can find us like this in social media, and I want to give a special thanks to all my team members. Y recuerda, toma pulque y come nopal, que la próxima semana otro video se va a lanzar.